So now if we get the system curve, so based on the system curve, we will select that how much of net positive suction head should be required for the pump, and how much input of a water of a power should be required for a pump, as well as the head required, and similarly the for the capacity of a system, based on the capacity of a system and based on the head required. So these property are determined. So basically based on just drawing these perpendicular lines, we get these type of uh, different size of a pump, the Q, H, similarly efficiency, and the NP, SHR, and the power. So these are basically the different properties of a pump that based on which you have to select a pump. So now to calculate that whether the cavitation will occur or not in a pump based on this data. So how much suction left should be kept for in order to avoid the cavitation problem in a pump. So now calculate the velocity at the suction side based on the discharge and die of a pipe. Total loss in suction line by multiplying 2 with the velocity head as given in the question. We have calculated the net positive suction head, and at 60 °F the pressure, the suction pressure is about 0.26 psi, and the atmospheric pressure is about 14.7 psi. So what should be the suction left? So by just putting these values, you will get this value. So what it means, that if you select the pump, then the suction left should be equal to 0.94 or less than that. If the suction left, if you kept this pump greater than this suction left, so the cavitation will be occur. So sometime if we if the pump is not fulfilling the head required for the system, then what we will do, we provide a pump in a series, or if you require if it requires the higher volume a volume of water to a specific point at a same height, so we usually provide a pump in a parallel. So sometimes there are several parallel branches with each branching containing several pump in series that are housed in lift stations. So these basically the pumps are provided in a series in order to get the head. So mostly in a high-rise building, for example 30-40 story building or higher than that, what it does that at, for example, at 10 story a pump is provided, at 20 stories a pump is provided, at 30 stories the pump is provided. So basically the pump left the water up to that point, and from that point this pump provided head and reach it to the transfer it to this pump, and that based on, and this pump then it is transferred to the that 30 story of a building. So basically pump in series is provided in order to get the specific head required for the system, and the efficiency for the pump connected in a series is calculated based on this formula. The total head provided divided by the head provided by each pump divided by the efficiency of each pump. So basically this is the pump curve characteristics curve for each pump. So by providing adding this pump in a series, it will get you this black line of a pump characteristic curve, and these are the efficiency curve for the separate pumps. So by adding these two pumps in a series, it will give you the efficiency curve in this form. So you can observe that for the system curve, it providing lesser value, while combining in a series, it will provide higher head, the higher flow rate. Similarly, pumps are provided in a parallel manner or a branching manner in this way in order to provide flow rate of a water at the same head having required higher flow rate of a water. And check valves are mostly provided in these pumps in order to prevent backflow. So parallel arrangement is necessary when a single pump will not efficiently provide a required discharge. So basically pumps in parallel is required for a discharge. Overall head is not materially affected. The total discharge is the sum of a discharge of the lines with individual pumps. So during of a slack demands, for example, at the night period, one or more of the parallel lines can be shut off, providing more flexibility to the system. So the efficiency of a pumps connected in a parallel manner has, can be calculated by this equation. Sum of the discharge through each pipe and dividing the sum of the discharge of at each point dividing by the efficiency of that pipe. So from the curve, you can observe that by providing the pump in a parallel manner, it give you this pump curve with the parallel combination, and by shifting efficiency curve in the horizontal direction. So selected pumps may not be suitable after certain time. So net positive suction head and vapor pressure change due to warm weather condition in higher altitude regions. So if you want to design a pump in higher regions, for example, in Nakawan, Naran, or a Chetral like area, then you have to consider the weather condition as well and the pressure condition. Because higher the altitude, the pressure decreases, so the cavitation problems in pumps occurs more oftenly. So centrifugal pumps need priming, vibration, noise in the pump system, cavitation, water hammer, mechanical defects. So these are different types of problems that can cause the vibration and noise in the pump system. So that's all about the pump. So now I will show you something in the WaterGEM. First of all, in the previous lecture, I didn't design patterns to each junction. So today I will design a patterns to each junction. Now I will convert it to the GIS demand. Minimize these. Okay, the demands has been assigned to each node. Now I will assign a pattern to each node. So first of all, I will define a pattern. So I will go to the home tab. In the home tab, select the patterns and then create a pattern in the hydraulic folder. So basically, diagonal patterns are provided in order to design, for example, We usually provided water throughout the day. So therefore, based on that condition, we should you should provide a diurnal pattern to the each junction in order to check the behavior of a pressure at each junction throughout the day. So basically, I assume some of the values because in Pakistan, there's no such research has been done by the researcher to uh, calculate the diurnal patterns for different regions. So based on my assumption that most of the, for example, for 4 to 9 p.m., the discharge mostly higher, mostly the prayers and going of our children to the schools and of people to the offices. So at the morning time, the demands of water are very higher. After that, the demands decreases, and at the 11 to about 2 to 3 p.m., the demands again higher due to prayer activities and other activities, mostly uh, coming of a children to the home, utilizing water for the bathing purposes and mostly for the cooking purposes. So in this region, mostly the demands was higher, and also similar at the night time, the demands also goes higher, and the demands mostly at the night time from 12 a.m. to about 4 a.m. the demands is very low, and also after 10 p.m. or 11 p.m. the demands also goes to decreases. So based on that, I assume some of the values for our region mostly, but mostly in the case of, for example, if you want to design for Karachi, so it mostly from the demands mostly goes higher from the 4 p.m. to the night of 1 a.m. or 2 a.m. mostly because mostly the factories and other businesses activities occurs at the night time in Karachi. So based on that, you have to manage these diurnal pattern for that area as well. So I will just copy. So here, that's okay. These values similarly. Okay. So now you can observe the curve behavior. You can also make it continuous. So if you know about the daily factors and similarly for the monthly factor, you can also assign these values. So for the daily factor, I took about 1.5. So I have already multiplied that value with the demands as I shown you in the previous lecture according to the design of WASA, design criteria of WASA. So and I left the hourly factor peak factor because I have to assign a diurnal pattern. So it included in this diurnal pattern. So I'm taking the start time of a simulation is about 12 a.m. and I will also change the calculation option to the from steady state to the extended period simulation for about 24 hours, having a hydraulic time step of 1 hour. And if I require reporting times, and though I can get it for any time of interval, for example, for a 5 minute, for a 10 minutes, so I can get that values in a report tab here using these steps. So I'm starting a simulation from 12 a.m. So I have designed a diurnal pattern Now after that, uh, I will select a pump by trial basis. So whenever you have to design a tube well, first of all you have to select such an area in your vicinity of a community that have open spaces. So it should be a park or a ground in such a way that you are able to design a tube well properly, because you will have required a separate pump house, and that pump house you will set all of your machinery, so that should be in open spaces. So I'm selecting this area. So this area is basically appropriate for designing a pump by placing a pump. So to place a pump here, first of all I will take a reservoir. I will place a reservoir here, and then I will connect this reservoir to this junction through a pump. Right click, pump. I'm placing pump here, and then connect this pump to this junction. Okay. So one point to remember, that here the pump I'm assuming it a mostly in a tube well, a submersible pumps are used. So in this figure, you can observe this is a submersible pump, basically mostly used in the tube wells, which we submerged in a well in order to get the pump the water. So mostly in a tube well, this pump is submersible. So in order to model in a WaterGEM, I will give you a smaller length and higher dia of this pipe at a suction side in order to avoid the head losses, because at the suction side mostly no head losses occur in a submersible pump. So I am taking it to the 1000 and length of a year. I am taking the user defined of a 1 meter. Okay, and this pipe size should be of 300 millimeter of a ductile iron pipe. So the pipe material you can change by yourself. So this here I'm giving a demonstration. Now, what type of pump and what type of pump characteristics curve should be selected? So for I want to show you that okay. For example, this is the water level in a well. So I'm assuming here that the water level from the ground level is about 200 feet below. And also when the pump, submersible pump sucks the water takes a drawdown behavior, shows a drawdown behavior. So I'm assuming a drawdown of 50 feet and taking a 10 feet of factor of 20 feet of factor of safety to keep a pump below the drawdown area. For example, if the drawdowns occurs such like that the pumps remains above the drawdown area, drawdown curve, so it will not suck the water. So therefore, I have to keep it in such a place. If the drawdown occurs when the pump sucks the water, then it should not cause such complications for the system. And other point, so it is the total values become 200 feet, 250 and 270 feet, and we should have let's first assign the elevation to this reservoir as well as this pump. So the pump should be off here. Slide. Okay. Using a Trex tool, model spot elevation. Let me create selection for these two, reservoir and pump. Right click, create selection set, pump and reservoir. Okay. Now I have to assign elevation to these two specific elements of a water supply network. I will choose these values. I will select selection set from here and I will select the pump and reservoir. Okay. So it will give elevation to these two elements. So now I have calculated elevation of this amount for reservoir, but in a reservoir we will give basically the elevation of water. So the elevation of a water in a tube well, in a well, should be in a groundwater, it should be of 1139 meter minus 200 feet. So first I convert into the feet, then let me check it. 4 minus 200. This main value is equal to 3737.31 foot minus 200. Okay. So this is the elevation of a water level. So I will just put this elevation in here. Okay. And what should be the elevation of a pump? Minus 270 feet. Okay. 50 feet, 200 feet below ground of 200 feet is basically the level of water below the ground level, and plus 50 feet of a drawdown and 20 feet is taken as a factor of a safety. Copy this value and paste it here. Okay. Now I have calculated the elevation of a pump as well. Now I will calculate the difference between the pump or the reservoir level, the ground level where the tube well will be designed, and the highest point in the water supply network. So first of all, I will check the highest elevation point statistic, which is the maximum value of speed. Okay, let me put it here. The water level, pump level, or highest junction level. Okay, so now what I have to find, I just I think the pump and the reservoir level, ground level should be same. Therefore, the equal to this minus 27. 346731. 3467. That much difference. Okay, 3467.31. Okay, so I have to find the difference between this and the highest junction level, which is about minus. So 84, there's a difference between the level of reservoir where we have placed a reservoir and the highest junction at the highest elevation of a junction of the water supply network. So what I will have to do, I will just add this value plus 27 feet where I have to place a pump below the ground level. So I add this, so we get the 354 feet of pump head required for the system, and similarly also add some head losses that will occur through the system when water flow through different pipes. So I'm assuming a value of a 30. So plus 30 feet. For example, we will have first to assume in order to find appropriate pump for the water supply network. So this is basically the total head, head for required for the pump and the head plus head losses required for the pump. So the total dynamic head required for the pump. So 384.87. So based on this value, we will check the pump in this curve, convert it into the meter, or maybe the foot may be available. Some unit की दी Okay, these are basically in the feet. So we will be required, and also let me some definition is not different. Okay, so what is the value 384? So let me select the 394 so 120 meters. So let me select this pump for 120 meter of a this curve 9 number curve. Okay, so I will put the value of these curves in the WaterGEM. So I have to define a pump definition. So I will create pump definition. Here I will, so these are different methods in order to define a pump head curve. So I will define by multiple point. Okay, it will take some time. So basically liter per second I will say. Change it to the liter per second. Okay. May cause some wrong selection as well. So let me use this design one point. So I will just take 120 394 feet required for the how much flow? How much flow will be required? For example, gallon per day. So how much value will be required? Let me check here in the demand. For example, the too much value. So there is a go there. Yeah, good car from definition. Pump भी आना. Da. 33. Hay que غالبا un video غلط ورک کړی و. Okay. 33 liter per second. پمپونه خو فکرونه کی gallon per minute. دې سیستم له ودا پمپونه کمزوري خیر زه به سواب الزام اوس پکې داسې ټایم خرابېږي efficiency curve value efficiency value 80%. So for this water supply network, these pumps are not, these curve are not appropriate to use. So I'm just assuming the flow value based on this demand. If you have to put values in the efficiency curve, you have to put value design flow of capacity of these value. For example, if you are using a liter per second, then this value should be put in here in order to design a pump. Here I'm just assuming that that much of head will be provided by a pump of flow of this value. So if the pump curves are not fulfilling the demand, then you have to acquire another type of curves from a company or from a manufacturer in order to get fulfill the your requirement. So here I'm assuming 80% of efficiency. At the waste efficiency font will be at 25, for example. Okay. And PCH is not required because it's a submersible pump motor, but it's okay. Other things are okay. Now define the pump definition for that pump and then run the simulation. Now, so these are basically the flow demanded at different type of interval. Okay. Let me also assign the demand diurnal pattern to each junction. I didn't assign these diurnal patterns. So I will go to the junction table. Right click, add column, demand and demand connection. Okay, to design one bound the difficult, let me go to the demand control center. Here the demand control center. Demand control center. And here just right click on the pattern demand, global edit, set to the hydraulic pattern you have defined, and then OK, close, and run the model. Okay. So these are the demands at different time of interval. Now let me check pressures. at each node. Annotation or color coding. Pressure. Converted into the PSI. At some point, the pressures are very high, so I will define by myself. 20, no, 10 psi, 20 psi, 50 psi, 80 psi. To add a time browser to check the values at each time step. Okay. خلیل بھائی خوب خو نه درځي. جی کلاس بس ختمو ملک شاندا یو دغه درته خیم جینو.
ٹھیک شو بس فی الحال خو ورته ناست یم که بس خوب ته قریب یم.
سید تنګ خو نه یې؟
نه ګورو ورته ناست یو.
دا وزو ریزلټ شو کوم او پته چې دی کې هغه کلر کوډینګ نه کوي.
یو ویلیو ډیره ګریټر ویلیو نه وه تا ویل چې دې نیټورک دپاره دا کار به نه کوي دا پمپونه. اخکې ما څونه خیال دی د ایکسل شیټ نه تاسو کومه ډیټا کاپي کول هغه ډېره غټه ویلیو وه پر ډے وه ما څونه خیال دی میټر پر سیکنډ کې نه و.
نه هغه بیا نو خیر دی ما بلته بدل کو کنه هغه زه پوه یم خیر دی جی صحیح وه. اوس دې کې څه نوټس باندې ډېر زیات هائی پریشر را روان دي په څه باندې چې کم دي. اوکې دا د انوټیشن کې څه مسله راغلې ده؟ زه احمد بھائی بس دا باندې کاپی دي کې دا انوټیشن دا مسله زه لږ سیټ کوم چې دا صحیح نه راځي، کلرینګ صحیح نه کیږي.
ٹھیک شو صحیح دی جی
صحیح ده جی. بس دا ریزلټ سو بیا سبا ان شاء الله 4 بجې کلاس کې به ډسکس کوو.
ٹھیک شو بدا ډیټا بم بیا لکه ما ویل ایکسل شیټ ته به څنګه کنورټ کوو هغه بم بیا سبا وکړو
اوبه سبا وکړه بیا پاتې شوه.
ٹھیک شو صحیح دی
زه صحیح ده. السلام علیکم.
وعلیکم السلام